Welcome back, everybody. So we will continue our discussion of monodromy from last week. We have today's session, Thursday's session, Thursday's coding, and then we move on to, I believe, witness sets. Okay. So hope you all had a good weekend. Let me remind you a little bit of the story that we've been telling in this chapter. It all begins with a so-called branch cover. But if you don't like thinking about branch covers, that's fine. It all begins with a parametrized polynomial system, which is squared. And so it satisfies the parameter continuation theorem, which says that there is a proper subvariety of the parameter space, for which outside of that variety, the fibers have some well-defined number of simple regular solutions in the upstairs. Because what is the story here? Okay, so I got some polynomial system depending on x's and p's. I guess maybe h or f would have been the kind of such parameterized polynomial systems we see. And great, so if I project down to the parameter space, how do I interpret fibers? Right? So how do I interpret the pre-image at some point in here? I think about it as somebody having emailed me a bunch of parameters and saying, solve this polynomial system over this parameter, and then I do. Now, of course, upstairs, these aren't really the solutions, they're the solutions, comma, u. But they're identified with the solutions. And we'll call that big omega u. All right. That subvariety where parameters within the subvariety we may not have these solutions in the fiber is called the exceptional set. We've been calling that capital delta. Okay. We have a generically d to 1 map from some variety, which I want to be irreducible down to some parameter space. We haven't talked very much about how to show something's irreducible or anything like that. So don't fret if you're like, I don't know how to tell something's irreducible. That's okay. Just right now, for the sake of theory, we're going to assume this thing's irreducible. And we'll use script u to denote all the nice parameters. So here nice means not in the exceptional set. So I indeed have the regular solutions in a fiber over any of my nice points. That script u is called a set of regular values of this map. Okay. You'll see two more gadgets written in this cartoon. Two loops, which start at u and end at u. Okay. The first one we call gamma. And just from looking at this picture, you can tell that I can shrink up gamma continuously until it's just a constant path here. In other words, I would say that that loop is homotopic to a point. So being able to continuously deform these loops and all the ways in which one can do that gives you the homotopic class containing that loop. Here's a loop, lives in loop space. We haven't really introduced this notation. This is just all loops in U based at little u. And we really, theoretically, we think about this, right, as the class of all loops under homotopy equivalence. And then there's this way to take such a class and to extract a permutation of the fiber. And it's the thing we've been doing in all the previous chapters. It's homotopic continuation is the way to do this. Now, you don't do it on the class because this is an infinite object. You can't represent infinite objects on a computer. You do it for a representative of the class. So this is what's happening on a computer. So you take some representative of one of these classes. That gives you a loop downstairs. And you perform homotopy continuation over that loop. Now, since we've pretty much only talked about loops, homotopy continuation over like straight line paths, that's fine. You can totally hook up straight line paths and put them together to get loops. And that's indeed how this is done on a computer. You take like a triangle based at view. Okay, and then what happens is I take all my points in the fiber. Those will be my start points. The polynomial system parameterized by u will be my start system. And I'll take those start points, that start system, and I will solve this target system in a straight line home. So maybe I'll erase. Okay, and so each point can be tracked on its own computer. So I go there, and then I go from that point down here to this point. Okay. And then I go. Okay, so that's one path as I go around this loop. Now, wherever I started ended up being wherever I ended. And that's because this is a homomorphism. In other words, the trivial element here, the identity element, which is just the identity loop that stays here, will go to the identity element of this group, which is the thing that permutes nothing. It's just the identity map. And so since this can be contracted to a point, we shouldn't see any permutations upstairs. On the other hand, if we want to draw something that does look like it goes around the discriminant, in other words, represents something non-trivial in the fundamental group, unfortunately for my cartoons, we kind of have to like pop out of the real parameter space and draw something like this. Okay. So now if I try to shrink this string on gamma prime, I would kind of run into this bar, this rigid red curve. Okay, so I wouldn't be able to shrink it down to a point without passing it. That's the intuition. Now, obviously, this is in some k-dimensional complex space, but do this. Okay, and so what happens as I go around this loop, I do the same thing. If I wanted to, I could just do a triangle instead of a loop, but theoretically, I can think about a loop, and I might get some swapping of points. Here, I'll get a bijection from my start system, my start solutions, which is omega u, to my target, which is also omega u. So a bijection from a set to itself is called a permutation. And so I'll get some permutation of these points. And the way I've drawn this, I'm trying to indicate that the permutation that gets cooked up here is everything stays the same except 2 points get swapped. And that would be sigma gamma prime. Okay. So a priori, I'm just going to get a bunch of bijections from this solution set to itself. But it's really useful, especially on a computer, to give these solutions labels. So in other words, 1, 2, 3, all the way up to D. You're gonna have to list them on a computer anyway, so you might as well use the ordering of the array as the implicit label. And now, my sigma gamma prime over here can be written as an actual permutations of the numbers 1 through D. But that depends on my labeling choice. Okay. Any questions on that side? Okay. So who remembers from group theory how the labeling affects what permutation we write down? For example, rotation by 90 degrees of this graph will send 1 to 3, 3 to 4, and 4 to 2. So it's a fourth cycle. But what if somebody else labeled it differently? What would happen to this permutation? Good. So Kate says it's going to be conjugation. So in other words, this is Taylor's labeling, and this is Kate's labeling. It's going to get something else. And Taylor's permutation looks like case permutation. Except I'm conjugating by some permutation. And that permutation is simply encoding how Kate's labeling differs from mine. Okay, so Kate labels 3, 1, 4, 2, right? Then the way to do this change of labeling, I would have to switch 1 to 3. I would have to switch 3 to 2, and 4 would get to be the same. Okay. And so this is one of these tedious things you work out in your group theory class, that conjugation is really just related. Okay. So if I want to take a loop in my parameter space and I want to cook up a permutation that I can write down just as a permutation of the numbers 1 through d, that's going to be totally well defined up to maybe relabeling. In other words, if I get a 4 cycle like this one, I'm not going to like relabel something and get a product of 2 2 cycles. Okay. Another result you'll remember from group theory is that the conjugacy class of a permutation in the symmetric group is just all permutations with the same cycle. Why? Because if you wrote 2 permutations with the same cycle type down, you'd be looking exactly at the permutation you would have to do via relabeling to go from one to the other. Okay. Great. So G pi u is the image of this map. And so G pi u as a subgroup of SD is well defined up to related. Which makes it lovely for me to grade your homework because some of you will be writing down different answers, but everybody will be correct. It's up to me to make sure that your labeling is just fine. Okay. So. Okay, there's also this pesky base point that keeps showing up. This is annoying to keep writing down. You know, it seems to suggest that if I choose different base points, I might get different monodromy groups.
Why long as your point is in path connected complement, it should not matter.
Rajwell says something path connected, so it shouldn't matter. Okay, and yes, absolutely. So first of all, I am path connected down here, right? Because I'm the complement of a complex hypersurface. So my real one-dimensional loops will miss it. Being connected downstairs is pretty much exactly the same statement that the gamma trick works. That I can go from any parameter here to any other parameter via a path. Okay, gamma trick's a little stronger. It says a random path will work. All right, so if I want to go from G pi u to G pi u prime, I claim that this is also well defined up to some conjugation action. And I'm gonna have to create some map, which goes from G pi u to G pi u prime, an isomorph. Or maybe I'll do it here. Here's my u thing. Again?
Even you at the top, right? Why would
Yeah, thanks. Very good. So here's my u prime. So somebody gives me a loop in u. I want to cook up a loop in u. Okay? In some consistent manner. So if all of you give me different loops, I can consistently apply some map and I get some loop based at u prime. Okay, I'm going to take any path, how, from u prime to u. Okay. And so now if somebody gives me a u, how do I get a u prime? So if somebody gives me a path gamma based at u, how do I get a path gamma prime based at u prime? Well, I will do tau first. And then gamma, and then I'll go backwards along tau. And that will be based at u. So what is it? I go here, I go around, I go back. And now that's a loop based at u prime. Okay. Notice, all tau is doing is giving me some bijection between the labeling here and the labeling here. In other words, the only thing that changes when I look at the monodromy over this loop is that it's a relabeling. And it's a relabeling exactly by how tau identifies the labeling over u prime to the labeling over u. I'm covering a couple things under the rug here, but this is how you should think about it. So these taus are not loops based at u, these taus are paths. So I haven't really told you exactly what this means, but it is exactly this bijection here, identifying labels. And this will hopefully make more sense when you get your hands dirty with it on a homework. So choosing a labeling on your computer of the solutions will change the monodromy group by conjugation action. Choosing some other point and a fixed path between one base point to another will identify those two monodromy groups up to relabeling as well. And so we'll just refer to the monodromy group as G pop. We've already lost the game of having some canonical labeling of our solutions. So any such we'll call G. They're all the same. Questions so far? I guess what you give the name. It is the monodromy of the branch cover pi. Or if your branch cover came from the parameterized polynomial system, we might say it's the monodromy group of that parameterized polynomial. Okay, and at this point, depending on your background, you might feel a little bit out of your comfort zone. What does any of this have to do with actually solving polynomial systems and stuff like that? Well, we ended last week talking about the monodromy solve algorithm, right? Can somebody remind me the general idea behind how to solve systems via monodromy? What's the input to a monodromy solve?
So you iterate over a loop. No,
Like a loop or like a computer loop?
computer.
Computer loop.
Yes,
Okay.
you iterate over a computer loop several times, and then you see how different those points are from the original point or the start. start
Yeah.
a solution.
Great. So input is some parameterized polynomial system along with one solution over one parameter. So you gotta give me a u, you gotta give me one of these, and then you gotta give me the polynomial system. And over a computer loop, right, like for blah from blah blah blah, or while blah 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 blah, I will do path tracking over several random, like, topological loops. Okay. And every time I do that, I apply to all this, well, to this solution. And as long as the permutation corresponding to that loop doesn't fix this point, I'll actually find a different one. So maybe I find number 2. I could have found number 17 also. But you haven't chosen a labeling yet, so you might as well call it number 2 because it's the second one you found. And then you repeat that over and over again. And we coded it up where we just repeat it over and over again over 1. And then you can ask questions about like, how many loops do I expect to have to do before I find all the solutions? And as long as you make some pretty strong assumptions about probabilities and things like this, you can start to analyze this as classical problems from probability that already have answers. So for example, as I've given you, monodromy solving is just a coupon collector problem. Every time you shoot that solution 1 over a loop, you find a random solution, uniformly random. So how many of those trials do you need before you find everything? We said we computed it's an expected d log d. Okay, so now I want you to think for a little bit, maybe 5 minutes with each other or online. I will pause the recording. I gave you a very bad version of monodromy solving. What improvements could you make? Okay. All right, welcome back. Apologies, there seems to be some sort of construction happening a floor above us. So there will be a noise. We will suffer through it. So how do we upgrade this algorithm as I've presented it? Well, the first thing you can do is if you find new solutions, well, track those along with the first one. Why were we only tracking one along? You know, this will be able to take advantage of like parallel algorithms because we know homotopy continuation can be run in parallel. So if we've already found 100 solutions, we probably don't have 100 processors. So we can take full advantage by sending each solution to one processor for doing path tracking. Okay. Great. Other suggestions were, man, it would be awesome if we could predict anything about this fundamental group so that we could try to sample not just any old loop, but loops that will likely derange our solutions. In other words, move them around, not have a lot of fixed points, things like this. We'll talk a little bit about understanding the structure of these monodromy groups later. But I want to suggest one more thing. You might as well choose your base point to be real. As long as your triangles are still triangles in complex space, this isn't going to cause any problems. You can have one of your vertices of your triangle be real. You just can't have an edge be completely real, because then you might have to cross the discrete. Okay, what's a great thing we know about solutions to real polynomial systems? The non-real solutions come in complex conjugate pairs. Right, so somebody gives me a solution, I'll shoot it around, find something. But if the thing I found was non-real, I get to add its complex conjugate to it as well. Okay, so that's just another small little upgrade one can do. Great. Okay. So we have a definition of the monodromy group. For analyzing algorithms, we make some assumptions about it, but these assumptions are generally wrong. The first assumption is that the monodromy group is the full symmetric group. The second assumption is that we can actually sample uniformly from the monodromy group. And the third assumption is that homotopy continuation always works perfectly. In other words, we're never doing a loop around this and then accidentally jumping to something we shouldn't be because of path crossing or something like that. Okay. So great. So now I want to tell you an algorithm which will compute the Galois group correctly, and we'll discuss what the difficulty in that algorithm is. Okay. So in this picture, we should another color. We're gonna take a random line downstairs. Call that out. Okay. So what's going on? I'm gonna look at the branched cover for this parameterized polynomial system, if you will. Not over the whole parameter space, but just over this random line. Okay. So I'm gonna restrict upstairs to the preimage of L. And that's gonna land to L. Okay. Is this a branched cover? Okay, so what would we need for a branched cover? We need this to stay irreducible. We need this to almost be surjective still. Okay. Well, a random line will mostly miss a hypersurface, but it'll intersect it at some number of points. So the exceptional set in here is L intersecting this exceptional set. So all the points that were in the exceptional set before, but now are also in L. Okay. And this I will just say is irreducible. If L is chosen generic. If you have taken an algebraic geometry class, then you might recognize this as a Bertini theorem. And if not, that's fine. Just if you choose a random line downstairs, as long as upstairs was irreducible before, the upstairs will be irreducible when you intersect it with the preimage of that line. And since we generically miss the exceptional set, if I pick a random point on this line, I'll still have d points in the fiber. So this is still d to 1. So we've still got a d to 1 branch cover. We've just restricted it to some line. And there's a theorem by Zariski. Theorem by Zariski has to do the conclusion of some topological statement. Hypotheses live in the world of algebraic geometry. And it says that as long as you have chosen this line, so that the number of intersections of this line with the exceptional set is the generic number of intersection points, also known as the degree of the exceptional set, then you get this surjection of fundamental groups. Okay, and so the thing you actually care about, because this is not a topology class, the monodromy group didn't change. Why? How do you get the monodromy group? It's the image of the fundamental group. If I have something else, say the regular points on this intersection surjecting onto it, and these maps And so I can either take the image this way or take the image this way, it suggests. So image of this is the image of that. Monodromy group doesn't change. This is the thing to remember. Okay. If you're into Y, that's true. You follow this logic. Otherwise, you just know, as long as I have a branch covered, if I restrict to a random line, the monodromy group will not change.
Giving cardinality.
Yeah, thanks. Yes, I do. Thank you. Why is this so strong? Well, because of that exercise you did in your first homework. You know that the only proper subvarieties of C are finite sets of points. So now, this restricted branch cover essentially is going down to C. Okay. A line is just a copy of C. It means its exceptional set is just degree of delta many points. If somebody gives me some point that's not in delta, let's say I have P1, P2, to some P capital D. This is my U. I've drawn a bunch of loops. What are they? You go straight to one of the exceptional points, and then you do an itty bitty loop around it. Okay. Each of these is some element of the fundamental group of the plane minus a bunch of points. Okay, let me call them gamma 1 all the way up to gamma D. Okay. They form a generating set for the monodromy group. Okay. Because they generate the fundamental group.
Wedge of circles.
Yes.
Okay.
Okay. So what have I done here? So if anybody gives me any loop downstairs, right? So maybe I can go, whoa, that's a loop. Oh my God. Boom. Right? I can write that as a product of all of these gammas. Okay. Because the fundamental group of plane minus a bunch of points is essentially just a free group. Okay, but who cares, who cares, who cares? The whole point is I have just told you exactly how to get the Galois. Sorry, the monodromy group. I haven't said anything about Galois yet. I've just told you how to get the monodromy group. Restrict to some random line. Compute the exceptional set, which is a finite number of points. I can do that on a computer. Okay. Take loops, which go around each of the exceptional points just once. Do homotopy continuation over each of those loops. You'll get a permutation. And then take the group generated by those permutations. This will be your Galois, or your monodromy group. Now, is this a proof? Like if you do this on a computer, have you proven that something has a particular monodromy group? No. But where is the failure to be a proof? It's in the homotopy continuation. If you could prove that your homotopy continuation worked, then you would be able to provably compute monodromy groups.
Can you do that with numerical methods?
Can you certify homotopy continuation using numerical methods? So, but your question is, can you prove that homotopy works using numerical methods? Is that the question?
No. Never mind.
So you can prove that homotopy continuation works, there are methods. They're expensive. As far as getting these methods into like homotopy continuation.jl and stuff, that hasn't happened yet. We will have a section on certification at the end of this course. We will talk about the certification algorithms that do exist in homotopy continuation.jl. And I will discuss a little bit the idea behind certified path tracking, so certified homotopy continuation. As far as whether or not one would consider this a numerical method or not, I think is up for debate. What you end up doing in all of these certification methods is you kind of bound the numerical error by some symbolic stuff, and then you do some symbolic stuff to claim that paths didn't cross and stuff like this. So you do handle the numerical error in this way. I hope that answers the question. Otherwise, we can chat more after the recording's off. Great. So next time. Oh, and on the homework, you do this, by the way, on a computer. You computer monitor. Okay, great. So I will talk about computing these in practice and how this usually actually doesn't work in practice for large problems. I will talk about some other phenomenon which will cause the monodromy group to not be the full symmetric group. So one of our monodromy assumptions when analyzing these algorithms is that the monodromy group is the full symmetric group. There's some ancient wisdom that this is often the case, and I will describe a large collection of times in which it's not. I will say 2 sentences about why this monodromy group is a Galois group. And I will end this section on Thursday with a discussion of monodromy in the context of this witness set problem, which will lead us into the next chapter, sets. Their monodromy is full symmetric group, and there is a really cool stopping criterion for monodromy solving called the trace test, and that will lead us into witness sets. So thank you, and I'll see you Thursday.